All, I would like to thank Luke and all the organizers for the great job. And start with the disclaimer. This is one of the few experimental talks in this conference, but I will not bore you with technical details about the experiment. But if anybody is interested, of course, I can present you during the conference. Okay, this is my group, and in particular collaborator to this work Alessia Vella, Ivo De Giovanni, Marco Gramegna, Fabrizio Piacentini, and Enrico Retifano. Okay, so what is the point? Actually, I'm going to present you some new experiment where we've used weak measurements for measuring the bell parameter on a single pair. And then I will discuss some implication of this work. So maybe it's worth just to mention what weak measurements are. So this is a new paradigm of measurements in quantum mechanics introduced by Aronoff, Albert, and Byman already several years ago. And the idea is to have a weak coupling between the pointer state and the observable. So you don't obtain in this way a perfect information of the observable, but also you do not cause a collapse of the wave function, but just a small decoherence. So you have this trade-off between a partial information on the observable, but also only partial decoherence of your state. So this is, of course, very different from projective measurements where you totally collapse the state, but you also have a perfect information on the observable. So what are weak measurements for photons, in particular for polarization? So the idea is pretty simple. When you have an optical beam, okay, in the usual projective measurements, you use for the polarization a birefringent medium, and you perfectly separe extraordinary and ordinary beam. So you have perfect information on the polarization. In the weak measurements for polarization, what you do is just that you have a partial separation. If this is the single photon, this is just the profile of the wave function of the photon. So in this way, you cannot really have perfect information of the observable, but you also introduce only a small decoherence. Okay, so since you do not collapse the state, at least not totally, but you only introduce a small decoherence, eventually you can perform sequential weak measurements on the same state. And this can also be done in observables which are not compatible. So, for example, in two different polarization bases which are not orthogonal each other. So this was proposed by Popescu and others, and we realized these sequential weak measurements already a few years ago. Okay, so the idea of this talk is to apply weak measurement on a single entangled pair of photons. So the idea, of course, of Bell measurements is that you have you produce entangled photons. And usually, in a usual Bell experiment, you measure polarization in a different basis on the two photons, and then you make a correlation between them. In our case, we perform sequential weak measurements on the two photons, so we can extract partial information on the polarization on a non-orthogonal basis on both the photons. And as I will discuss, this allows to measure the Bell parameter on a single pair. Okay, so there has been some previous work in this direction. For example, by Padua group considered weak measurement on a single arm only, by the Valencia group considering just one weak plus one strong measurement. Some Legge-Gard inequality was measured by White and others in superconductors, but no complete measurement of the Bell parameter was performed up to now. Okay, so of course I think it's not really needed to introduce Bell inequalities for this audience. I just mentioned very directly what they are. So the idea is that you have just entangled pairs and you make measurements on Alice and Bob's side, and then you make a correlation between the two measurements, and at the end you obtain this parameter. What is interesting is that, of course, Bell demonstrated that this parameter, the Bell parameter, is bounded by 2 when you have your measurements are predetermined by some hidden variable, and you exclude non-local correlation, while for a suitable choice of your parameters, this inequality is violated in quantum mechanics. So this is a really beautiful result because allow to test a standard quantum mechanics, not only respect a single alternative theory, but with respect to a whole class of alternative theory against every local deterministic theory. So when you have a theory where the results are predetermined and the theory is local, you must respect this bound. If you observe a violation, you exclude all this class of theories. Okay, so these are the hypotheses in Bell theorem. So the existence of predetermined value, the Bell locality, and the third hypothesis is independence of measurements. Sometimes it's called free choice, but free choice is already, from a philosophical point of view, a little bit different. Independence of measurements. So Bell proposed this inequality in 1964, and as you know, the Nobel Prize was awarded in 1922. So it was a long path for realizing these experiments. Why was this path so long? Because you must respect this condition, and this leads to, in the experiments, to the possibility to have loopholes. In particular, for example, if you do not detect enough pairs, you can have the so-called detection loophole, namely, you don't have a fair sampling of your hidden variable if existing, or you can have problem in having space-like separation of the two experiments. This is the space-like separation loophole. And also you must have a random or a freedom of choice of the experimental setting that should be independent. So if you do not realize exactly this condition, you have these possible loopholes. And this was the reason why the path toward a final test was so long, but at the end there were, of course, some intermediate steps. Closer realized the first experiments with photons and the experiment at all, but no loophole was eliminated. The Orsay group eliminated the space-like separation, but they were detecting a few pairs over 10 million, so the detection loophole was still very important. And at the end, 3 groups, and Anton Zeidler was one of these groups, realized the final experiment without any loophole. So, at least one of the conditions of Bell inequality should be violated. So, either we have the universe has no predetermined values for the observable, or locality is violated, or freedom of choice is violated. So if you still wanted to build a theory going beyond the standard quantum mechanics, one of these conditions must be violated. So you can think of non-local hidden variable theories. For example, de Broglie-Bohm is one example. Or you can have superdeterminism, eventually at Planck scale, or you can have even a more exotic idea for violating non-locality. Okay, so this is the situation in this moment, but some discussion emerged about the fact if there is an hidden hypothesis in Bell theorem, and this is the so-called counterfactual definitiveness. What is counterfactual definitiveness? In usual experiments, of course, you cannot measure all these correlation functions with a single pair, because you are making projective measurements, so you are measuring on one pair this correlation, on another pair another correlation, and then at the end you build the Bell parameter. So the counterfactual definiteness is the ability to speak meaningfully of the definiteness of results of measurement that you have not done. And somehow it seems that since you must perform these measurements on independent pair, you should suppose that if you have used this pair for another measurement, you have obtained the same result of correlation that you have not obtained for another pair. There was a long debate. I'm not entering in this discussion, but for example, one affirmation was that since it's not possible to perform more than one measurement on a particle, in particular the photons that are annihilated, so etc., etc. So what we have demonstrated is that one can go beyond this point and making a band test with a single curve. So this means that you do not require any counterfactual statements, and also this is just for quantum technologies I mentioned, is also useful method for testing entanglement without deteriorating this. Okay, so which is the idea of the experiment? The idea of the experiment, I generate a psi minus, so a state entangled in polarization, and I perform weak measurements, sequential weak measurements on both the photons, and since I can get at least partial information on this polarization on both the photons, I can obtain all these correlation functions on a single pair. Of course, the single measurement is very, very noisy because I only obtain a relatively noisy information on the observable, but when I average over several pairs, I have a clear violation of the value equality. Okay, on the other hand, if I look to the single pair after the measurements, I see that the deterioration of the due to the decoherence is rather small. The fidelity respect to the psi minus, which was 99% before measurement, is decreased to 96% after measurement. So I have a very small decoherence of the system. Okay, I can also measure the Wigner inequality, which is just another kind of value inequality. But what is interesting is that Wigner inequality can be rewritten in terms of probability of the detection of the photons with, let's say, a dichotomic 1 or minus, 1 or 0, plus or minus, as we want to define, with respect to the polarization. And this can be done just by, I do not enter into the details, but what you have a quadrant, and so your photon is arriving on this detector, and according to the quadrant where you are measuring, you are attributing the value for the polarization in the two bases. Of course, you make some initial calibration procedure. Again, I'm not entering into the details, but at the end, these are just preliminary results, so you can reconstruct this probability, and what you observe is that you have negative probability, and this is the another clear way of seeing that in quantum, you cannot interpret this correlation as classical probabilities. And the fact that you have this negative probability means that you cannot introduce classical probability for describing these correlations. Okay. And okay, this is the violation of the Wigner inequality. Again, it's preliminary results. I would like also to mention that our experiment, of course, at the moment is not loophole-free. We are just looking to the possibility to make a test of the band parameter on a single pair, but so eliminating this discussion about counterfactuality, but in principle you could go in that direction. Okay, so I think these are several implications. So by removing the need to choose among the different measurement bases, our approach stretches the fact that counterfactual definiteness is not a necessary hypothesis for that test. So it eliminates the discussion on counterfactual arguments. And this just for mentioning that even recently there were papers mentioning that since it's impossible to measure with different angles setting at the same time plot, introducing these contrafactual arguments, I think all of this is overcome by our experiment. Also, it stimulates the discussion on the significance of certain interpretive scheme. For example, modal interpretations. Modal interpretations were proposed by Dick and Van Frassen, and now, for example, Philippe Granger is proposing a new elaboration of these schemes. They have the ambition to build quantum mechanics as an objective, observatory independent description of physical reality. In their interpretation, the mathematical states represent situations with definite physical properties, even if the state is a superposition of eigenstates, because the assignment of properties depends on the context, including also the measurement apparatus. So you have to consider both the state and the context. So you can try to do this. These are the modal interpretation, but the point, of course, is that these, in our case, we don't have this context different for incompatible observer. In user band test, you are making the measurement of the state in a context for a specific polarization basis, then repeating the experiment with another polarization basis, and so on. In our case, the context is difficult to be defined because we are measuring incompatible observer, of course, at a weak measurement level, but at the same time. So I think this is something that should be solved in this kind of models. Of course, our experiments also cast questions on this non-Kolmogorov interpretation, the test asserting that they path incorrectly statistical data on different incompatible sampling experiments into a single probability space, because of course in our case we are measuring all the observable at the same time, so that I do not see how one can come back to this point. As I have already mentioned that our experiment also is a method for characterizing entanglement in situations where one disposes as a result of several identical entangled pairs. So instead of just consuming part of them for testing if they are faithful to what you want to have, you can use all of them with a small deterioration of the single system and to test if these are faithful results. But okay, this is for quantum mechanics. Okay, so this was a first experimental result. The second experimental result is connected to a proposal of Eliyahu Cohen and Carmi, and it connected to look to what really quantum correlations are. So, as you probably know, of course, quantum correlations are limited, for example, for what concerns binary inequalities by the Chillerson bound. But if you only impose non-signaling, actually like in a Popescu box, you can have correlations which are stronger than quantum and do not violate signaling. And in this case, the limit for the Bell inequality would be 4. So in principle, you can have correlations stronger than quantum mechanics that are not violating signaling. And so the point is that is there any further principle, fundamental principle, ruling out stronger than quantum correlations? There have been several works in this sense. I'm not going to detail them. One idea that emerged in this paper is that a possible principle is that one should have the so-called relativistic independence. So local uncertainty relations cannot be affected by space-like separated parties. So measurement of Ellis cannot affect the observed uncertainty of both. So what you can do, and was done in this paper by Carmi and Cohen, is just to consider the cross covariance matrix of the measurement of Alice and Bob. And you have a local uncertainty relation on any side, for example. And you can derive generalized uncertainty relation by imposing positive semi-definiteness to the submatrix of this correlation matrix. And if this parameter R depends on the measurement of Bob, this means that Bob can influence generalized uncertainty relation. So to impose the condition that you cannot have this effect leads to this inequality. Here is the Bell parameter, so this inequality is including some non-local and some local part, and this is the limit of this measurement imposed by this relativistic independence. And indeed, you can look to this inequality. This inequality requires measurements on incompatible observable. So this can eventually be performed with weak measurements, and so it's set up similar to the previous one. Against, you are producing a psi minus, so you have sequential weak measurements, and you can collect these measurements for measuring the correlations appearing, of course, in Bell parameter, but also these uncertainties. And okay, we can have an angular mismatch with respect to the one saturating the Chirelson bound, and you can plot our experimental data respect to this mismatch, and you can see you follow the theoretical cubes and you saturate the inequality without, of course, violating it. So in agreement with the prediction of relativistic independence when you don't have any mismatch. What is also maybe even more interesting is that you can decompose the two part of the correlations, the non-local part deriving related to the Bell inequality and the local part, and you can see the data extracted for these two parts in agreement with what predicted by relativistic independence. Okay, so I try to be a little bit fast also for leaving time for discussion. So here are my conclusions. So actually the message I want to have transmitted is that weak measurements are a new interesting tool for not only for quantum technologies but also for studies on the foundation of quantum mechanics, and they allow for new unprecedented capacities of measurement. And this can be exploited, as I've shown, for example, for tests of Bell inequalities on a single Bell pair that was considered impossible. Of course, this is impossible with the usual projective measurements. And also for new tests like this relativistic independence that I've shown in the second part of my talk. Of course, these weak measurements are also new tools for quantum technologies. For example, these results that we have achieved can be used as a method for testing entanglement as a resource that is relevant for the development of quantum technologies. Thank you for your attention.
Anticipating the questions.
How do you choose the initial state of an experiment? Because it's always assumed that it's statistical. That's, to me, a too vague concept.
Yeah.
It might be in deterministic theories that the choice of the initial state determines everything.
No, okay, of course we know we have this phenomenon, I don't have time to describe it, which is parametric down conversion. We know that in this parametric down conversion, the photons are produced at least in what is called type 2 parametric down conversion in cones of different polarization, but you have the two cones superimposed in certain directions. So in this direction, the amplitude are coherently summed, and you generate a deep C minus. So why to use deep C minus? Because you can also use C plus or any other base state. C minus is just an arbitrary choice. But you can also test that you are actually producing this state, and this is done by using what is called quantum tomography. So you take your state and you make different polarization measurements, and you reconstruct the density matrix, and you compare with the theoretical prediction, and you see that the fidelity of our produced state respect to the theoretical prediction is 99%. So it's very high. I don't know if this answers your question or.
I'm not sure. These are different measurements of the same system. Or?
Okay, the tomographic, no. The quantum tomography is performed on different pairs produced by the same system. So you are your source, you have different pairs, and you make a tomographic reconstruction. In principle, you can also make tomographic reconstruction by exploiting weak measurements. In this case, you can acquire all the data on a single system, of course with a very big noise. Then you have to average over several of them for having a statistical significance of your test. But let's say this is all the experiments performed with varying inequalities, for example the Zeilinger one, or the aspect one, or the Clauser, were done with states like this. So in particular, Zeilinger ones, Kwiat ones, and all the experiments with now in quantum technologies are using this kind of results, which are these photon entangled pairs producing parametric down conversion.
More questions? Yeah, actually one, if there is enough. So about the measurement of entanglement with weak measurement.
Yeah.
So do you need to repeat several times and then you get a good estimate of the entanglement and your state is still there, if I understand well, or what? Are you getting one shot?
No, okay. The point is that you have a pair,
Yeah.
you make a measurement, and you obtain for a single pair a value of the Bell parameter. But this measurement is very noisy. So the Bell parameter can even be outside the physical range as any very noisy measurement. In order to collect, let's say, a sample sufficient for having a clear violation of the Bell inequality, you should use different pairs. But at the end, the point is that you have obtained a noisy measurement of Bell parameter on a single pair, but you need, of course, to have several pairs for having a statistical significance.
Yeah, because I think you were doing successive measurements on the same pair.
On the same side. These allow to obtain
That's not good for entanglement.
No, the point is that when you use the single pair, you obtain the Bell parameter with very noisy, but you deteriorate the state very, very little because your fidelity is decreasing from 99 to 96. So you still have a very good entanglement on the single pair. But what you have obtained is a very imprecise measurement of the parameter. Of course, otherwise you would violate the Heisenberg principle. You cannot obtain a precise measurement at the same time, or incompatible observable at the same time. You can obtain an imprecise measurement because you are limited by Heisenberg principle.
Thank you. So I think we can close the session and go for coffee break and we can speakers again.